Okay. Okay. Welcome, everybody. So today is week 10, officially our last lecture. Today I promised we were going to do something more potentially, hopefully fun with these amplifiers, BJT amplifiers. As I probably already anticipated, if not, I'm going to tell you now, what we do today is effectively not in the exam. Okay, what we do today, I'm going to tell it to you just, for curiosity and to complete, the discussion about amplifiers. So basically, if you're watching this video in the future, what I've just said may not be true for you. So check out with me before you do anything else, okay? So today is the 2nd of April, 2019. If you are in the future, this may not be true for you, okay? Sorry? So last week, we did the BJT amplifier in common emitter configuration, and we've seen the three common emitter configurations. One was with fixed bias, we called the C1. Then we had the C2 emitter bias, and C3 voltage divider. So these are somehow the three parts up to this point, let's say, is what we should consider examinable, okay? Just because, if you show that you understand how these operate, for me is okay. I mean, it means you understand how the BJT amplifier works. But there is so much more in the BJT amplifier, and I will show you in a moment. That's the aim of today's lecture, is about opening our eyes on this, we now open the door onto something that is immense. So if you remember, let's summarize our journey. We started with just linear circuits. We then went to semiconductors. We understood the semiconductors. Thanks to that, we then understood the p-n junction. Thanks to the p-n junction, then we understood the BJT. And today I will show you how, now that you know how to use the BJT, you can make effectively any amplifier you want. But most importantly, we will see that the BJT is also the key element of the, an element that you probably have come across, which is the operational amplifier. And so that's something we will briefly mention also later. So just to summarize what we've seen last time. So when we talked about C1 fixed bias, so you remember the configuration of, I need to hold these things. Yes, this is much better. So the fixed bias configuration was, we had our capacitor, and then there was a resistor, and this was VCC, this was RB, RC, and we were taking the output here. And this was V in. This was the fixed bias configuration. And we analyzed it. 2 weeks ago, I think we did the analysis in DC to see how to properly bias this thing. Last week we did the AC analysis using the simplified hybrid model. And the result was, for any amplifier you deal with, there are these 4 parameters that are very important. The input impedance, which in this case was, sorry, let me find it. So was RB in parallel to HIE. Remember, HIE is one of the parameters of the hybrid model. If you remember, this is the resistance, the input resistance of the model, which we said is roughly 1 kilo ohm. And then we have AV infinite. AV infinite refers to the fact that normally we would put here a load. So when the load is infinite, effectively we are not connecting anything. That's what AV infinite refers to. So, and we found out that this number was minus RC HI. HFE is the other important parameter. This is the current amplification in the AC regime, which is roughly equal to beta. If you remember, we've done this discussion last week over HIE. And in case you attach a load, the amplification becomes AV infinite time is the voltage divider with RL over RL plus RC. And current gain was we had also for the current gain, I didn't explicitly write it down last time, but it's useful also to write the gain in a similar way as we did here. So here we say, okay, let's assume that we have no load. What's the amplification? If you put a load, then it becomes that in function of this AV infinite when you don't have a load. Similar thing can be done for the current amplification. So if you look at the final formula that we found when there was a load attached, you can realize that you could split that formula in this way. Define AI0. I will explain in a moment what is AI0. RB over RB plus HIE. So this is so AV infinite was obtained when RL is infinite. AI0 is obtained when RL is 0. Is the short circuit current, which tells you effectively the maximum current you can get. If there is no load, it's a short circuit, that is telling you what is the maximum current you can ever get. That's what AI0 represents. And AI0 is this. And so in general, with a load of any generic value, AI will be AI0 RC over RL plus RC. And finally, the fourth element, fourth parameter that is important is the output impedance, which is, we've done it last time, we found out that was RC. So in general, for any amplifier, we are after these 4 parameters: input impedance, voltage amplification, current amplification, output impedance. And last week we also said, okay, if the C2, how was C2? The C2 this was with emitter bias. It means, is there a copy and paste on this board? It's all this with an additional emitter resistance with a capacitor, if you remember. So I'll try to quickly just redraw that. Okay, and we said that the reason why we have this capacitor is in such a way that when you are operating in frequency, in the AC regime, effectively this shorts RE and makes the analysis much simpler, because then the AC analysis becomes of this circuit becomes the same as that one in the AC regime, remember? Eh? And so you get the same, exactly the same formulas also for that. So here, C1, exactly the same. For the C3, which was with voltage divider, C2 emitter bias, we mean this one here, that is also, you may find it in the textbooks, in the references, because of this capacitor here, which this capacitor, as we said, has the role to bypass RE. So can also be seen as common emitter configuration with RE bypassed. Okay, just so you know. C3 voltage divider. The configuration here was, the circuit was this one here. Again, we have our emitter capacitor. I forgot your VIN, VO. And here is ground. So the only difference between this circuit and that one, so as we said, also here we have this bypassing capacitor for the AC analysis. So the real only difference is the presence of these two resistors instead of RB. And when we did the AC analysis of this, we realized, okay, these two will be in parallel. So you can use again the same formulas, simply replace RB with the parallel R1, R2. Okay? So that's why I find this, quite nice, because effectively you have three different configurations here, but more or less they use exactly the same formulas in the end. Just this thing to keep in mind. Okay. So in the post-lecture video last week, then, I had also mentioned some other, again, applications out of curiosity again. As I said, this is the part that I want you to, focus well for also in view of the exam. But then in the post-lecture video last week, I said, okay, what happens if I don't take this one in? This is would be the common emitter configuration, either in emitter bias or in voltage divider, but with RE unbypassed. Okay, so and there I demonstrated that that configuration is extremely interesting, because if you remove CE, you can demonstrate, I will not draw this again, but let's say without C, we can demonstrate that we can pick up either this or that. One of the two, they have exactly the same, similar properties in terms of formulas. But the most important characteristic, as I pointed out in the video, is that the voltage amplification is actually minus. So I think this is a very nice point to make. You see, in these configurations, we've seen all the quantities, with the exception only of the output impedance, depend on the hybrid model's parameters, either HIE, HFE, and so on. But here, for the first time, we see with that application there, we could see an amplifier where the amplification depends only on external parameters that I choose. So the voltage amplification here is completely independent from the characteristic of the transistor. I've got some circuits application in the end around these things. So we will come back to the, remember this is called RE unbypassed, with emitter resistance unbypassed. Okay, so today the idea was, I wanted to show you, obviously this is not the whole story, it's a very small window on, as I said, something huge. So I wanted to briefly mention to you, without going into the detail, I will upload, as usual, my notes for those of you that are curious and want to explore, the details behind the things that I will say here. I will not go into the details of the calculation. But if you want, again, you go back to my notes and you can later on have a look. So let me briefly present you a few more configurations that are quite important, just so you know of their existence. I will leave these formulas here just because we may need them later on. At least I will try to leave them. So another configuration that is quite interesting is the so-called common collector configuration, which is also called, well, it's mainly known as the emitter follower. Can you guess already what this emitter follower may indicate? Have you used operational amplifiers in the labs? Did you come across the term of a follower in terms of amplifiers? So a follower is an amplifier that doesn't amplify. It is only there to operate on other things, like the impedances. And that's what this does. This is a follower on the voltage amplification. So we will see, I mean, I want to do it here, but we can demonstrate that the voltage amplification is a 1. The circuit looks like this. It's common collector from the point of view of the AC analysis. So don't be surprised that actually it looks like that. And obviously, in case you wanted to connect a load, your load would be here. So this is extremely simple. Two resistors and the capacitors and the BJT. And you see the collectors connected straight to the power supply, the DC supply. When we go and do the ASC analysis of this, we said this must be effectively grounded. And so the fact that the collector is grounded, that's why it's called common collector configuration. Okay, and the interesting property of this circuit is that it has a voltage amplification of 1 or minus 1, let me see, 1. So that's why it's called follower. So whatever you have here, you will have it there. Actually, no matter, if I remember well my calculations, no matter RL, okay, which is also very cool, very interesting. The only reason why this could be there is probably to amplify the current. So you keep the voltage the same, but you amplify the current. So effectively what you're doing is you are changing the impedance of this circuit from input toward output. Probably the input impedance is high, so you have a very small current going in. The output impedance maybe is small, so you have a larger current going out. So this kind of operations, we will see in a moment. All these 4 parameters, input impedance, voltage amplification, current amplifications, output impedance, are all in the end extremely important when you start to see the bigger picture of this amplifier into a circuit, because each piece of a bigger circuit will interact with each other. We will see that more in detail in a moment. So emitter follower, and then I don't want to spend too much because anyway I'm not going into the details of these things. Let me see what else I have here. Yeah, obviously this is the emitter follower in fixed bias configuration. I didn't, because I've actually here the analysis also of 2 of them, also in the voltage divider configuration. Another one, interesting, is the common base configuration, which the property of this is that we can show that. I'll first draw it and then I will talk, because otherwise it's weird. So we have something like this, a power supply that we call VE. Then we have our BJT. So this is V in, and this is V out. Oh, and this is, so we understand why it's called common base. The base is to ground even in DC. This is VCC, sorry, this is RC and RE. So the nice thing about this circuit is that it has very, very small input impedance. The fact that the input impedance is small, it means that you can put a lot of current into this input. Okay? And another nice property is that the current amplification is 1. So this also could be called a follower in current. Oh, in my notes, I go through the entire analysis, and for all these things, I do calculate the input impedance, the voltage impedance, all these 4 parameters, they are all important. If you wanted to use any of these in a circuit, you need to know all of them. And the reason will become clear in a moment, in a few minutes. So, there is another one, maybe I won't. Yeah, okay, let's do this. So where is that? Okay, another circuit that is quite often found is the so-called collector feedback configuration. Feedback. When I was designing this course, initially I was thinking to do at the very end also feedback, which is basically would be in the beginning of then talking about operational amplifiers, but obviously I then decided very wisely to remove that because it would have been too much. But what I want to say is that the concept of feedback is very important. Feedback can be used to create stability, to make circuits more stable. And this is a technique that is widely used. Probably you've used it, and maybe you knew it, you didn't, when you were using operational amplifiers, maybe in the lab. Okay, so feedback is extremely important, and that's why I wanted to mention this circuit, because it exploits feedback. And the circuit is quite simple. So this again is V in, and this is V out. So the thing that is worth mentioning here is the existence of this feedback resistor. You can see goes from connects the collector with the base, and so the feedback, you can see it here in action when you think that if IC is going up or going down, this will be reflected into IB. That's how the feedback. So a part of the output is being returned into the input. Okay, and this process that creates increased stability. Of course, it can also become unstable, and that's why feedback. You need to. It's not for here, but if you were to go in depth into the analysis, you would realize that is negative feedback that creates more stable systems, while positive feedback creates instability. And can be used, though, in nice applications like oscillators, and so on and so forth. Anyway, so this was this nice circuit with feedback, and the last circuit that is worth mentioning before I go into a bit more details of how all these parameters combine together. Let's see, sorry, just a moment. What was that? Ah, there you go. So So in my notes, it's just the circuit. I'm not going into the details of the analysis of this. It's done very well in the reference I've given you. But this is the circuit, and it works, it operates as a differential amplifier. I will write down now the equation. Oh, sorry. Here, no, you have another generator. So this circuit is equivalent, if you have been, you have ever seen or used an operational amplifier, maybe you are familiar with this symbol for the operational amplifier, and effectively this circuit is equivalent to something like this. And in such a way that VO1 minus VO2 is a certain differential amplification, AV, time V in. It is a differential amplifier, which I think is also very interesting. With just two BJTs, we've now realized that with the BJT you can create amplifiers very simply. Now two BJTs together, in this configuration you have a differential amplifier. You amplify the difference between the two signals. And you understand that this is would be probably the first step of a real operational amplifier. And this AV is given by something like that. So it can be quite large. Remember, HFE is hundreds, HIE is 1 kilo ohm, RC, it depends what you've chosen. If it was 1 kilo ohm, you would have an amplification of 100 here. Okay, so differential amplifier. And so let me spend now some time to get you to reflect maybe on what we've just done up until today. So we've seen now, in depth, the common emitter amplifiers, all these other possible amplifiers, and there are many more that we obviously didn't even mention. But the final result of all this is that we've realized that these circuits are characterized by these 4 parameters. How can we use this? Can we create a model that can then be used to combine, for example, these circuits with other things, even with other amplifiers? So let's stay for a moment on the 4 parameters. Let's say that I want to create a voltage amplifier. So this voltage amplifier has a voltage amplification when I don't attach anything to it, that is AV infinite, has a certain input impedance, has a certain output impedance. From the point of view of the equivalent circuit, okay, we know that if you get into the details of what these parameters actually mean, they relate obviously to the actual circuits they came from. But from a model point of view, from an equivalent circuit point of view, I have a circuit that was, for example, that one that we had here, that we know has some 4 parameters Z in, AV infinite, AI 0, and Z 0. How can I represent that into a model, a general model? If, as I said, let's assume that I want to represent it as a voltage amplifier. I would do this. Black box, I don't care what's inside, I just know the 4 parameters. I will represent all the external parameters as we define them. That's my model of the voltage amplifier. This is a voltage generator with a voltage AV infinite time V, because it's been amplified. In the input, what I see is Z input, the input impedance of the circuit, because it's Z input that defines the ratio between these two, Ohm's law. Based on the definition we've used of Z0, the output impedance. The output impedance is defined. Why did I connect it like that in series? Because the output impedance, we've defined it as the impedance I would see from this point of the circuit if I was to assume that this side is at 0, the voltage is 0, or the current is inexistent. So if V is 0, this is 0, obviously it's a short, so what do I see? It must be Z0, it must be connected in series with the circuit. Because I know that I must see Z0 from this point. So that's why the connection must be made like that. So this is the model, the equivalent representation of the parameters that we've calculated into this equivalent representation. If I wanted to represent it as a current amplifier, I could do something similar. And here still V in. And this is AI0, I in. Why did I put Z0 like that, Z output like that? Again, same story. When I need to remove any generator on this side, so V in, if there was a voltage generator here, I should short it. So the current will be 0. If the current is 0, this is an open circuit. But from this side, I must see Z0. So Z output can't be in series with the current generator, because otherwise it would be an open circuit. I wouldn't see Z0, I would see infinite. So Z output must be in parallel to the this current generator. So this now is extremely powerful. We still haven't realized it, but now I have a model where I can put in the parameters of that circuit type, that implementation I thought about, be it the common emitter, the common base, whatever. And now I can start thinking even of combining the circuits. Okay. I got you interested now, isn't it? Okay, just a moment then. So let's, obviously these are equivalent, eh? because we are talking of the same effectively circuit. These parameters, Zin, AV, AV, and Z output, and AI come from the same circuit, are simply different representations of that, depending on what I'm more interested in, either voltage amplification or current amplification. So, how I go from this to that, it's the circuit itself that I've drawn that can tell me. I mean, from this input part, I mean, we can see that I in is V in over Z in. So if you were working with the voltage amplifier and you wanted to know what is I in, you calculate it. Or if you looking at this side, how much is IO? Or maybe better, how can we relate AV infinite, ZO, and AI 0? Let's do it on this side. By the definition of AI 0 is, as we said, the current that would flow outside if I was to short the load is 0. If I was to attach to the circuit a load 0. So if I do that, this load in parallel to Z0 makes Z output disappear effectively. So the entire current will flow in here. So there will be a short circuit current that is exactly AI0 I in. On this side, if I was to short, what would I get? What would be the short circuit current? I have this voltage divided by the only resistor or impedance existing. So it would be AV infinite, V in over Z output. So these two have to be the same, because they refer, this is the black box, is the same. It's just our way of interpreting things, that we assume that in here is AV and there is AI, but inside the black box is exactly the same thing. So these two have to be the same. And so you can write that by combining them, you can write that AV infinite over Z output V in must be equal to AI 0 I in. V in over I in is Z in, and so I can finally write that AI 0 must be Z in over Z out. So we've got a relation for the input and a relation for the output. And this allows us at any time to move from this model to that model, just changing the parameters in this way. And you can actually, if you wanted, again, for fun, you see this formula is telling us that these four parameters are in reality all related together through this formula. So you could, for example, for fun, check out that AI0 that we calculated to be for that specific realization, this value, this was the C1 realization. You should be able to check that Z in, which is this thing, over Z output, which is that, time AV infinite, which is that, should give you this thing. Okay. Okay, Okay, I will say this, and then we have a break. It won't take more than probably 7 minutes. I will remove, what do I remove? I remove this part. I remove this part and this part. I think I want to keep this formula. Do I need it? No. So I remove everything. Okay. So let us think now that we've now created a model in our mind of any amplifier. Once we have these 4 parameters, we can turn it into a voltage amplifier or a current amplifier. So let us think now. So imagine that I have an input here, and I have the bright idea, I need a huge amplification. I can't make it with just one amplifier. What do? I cascade. That's my initial idea. The idea is good, but we will see that there are lots of but. So this is stage 1, 2, 3, N. And obviously, in this connection here, we have that V output 1 of stage 1 is actually equal to V in of 2. And the same there, because of this connection. The output of one becomes the input to the other. And here is the key moment. We are talking about voltage amplifiers, so I'm expecting that in here, it's something like that, and in here, it's something like that. Have we seen already this circuit? Yes, has a name. What's the name of this very simple circuit? This is Z output 1. This is AV infinite 1 time V in 1. This is a voltage divider, isn't it? So the voltage at this point is the voltage divider between this Z in and Z output with that voltage. And so here is the eureka moment. I realize that not all the voltage amplified by this stage will end up at the input of the other, because there is this voltage divider in between. So it's only a portion of that. So really, V in 2, which is also, remember, equal to V output 1, is Z in 2 over Z in 2 plus Z output 1 time the amplification, the voltage here, which was AV infinite of element of the first stage time V in 1. If I was to take this one down here, this would represent the real amplification now of VO1 over V in 1 So what you see here is that AV infinite was the voltage amplification of this stage when nothing was connected. But now that I've connected it to something, the real, we can call this the amplification of the stage in the cascade, is actually being decreased now by this factor. This is because circuits are now interacting. through their input impedances and their output impedances. And so in the end, if we imagine that, I don't know, these are all voltage amplifiers with the similar models, we could write that so we could call this AV of stage 1, for example. And so the total amplification of the entire stage, if we had n of those, would be AV total is which is the V output n at this stage, at this point, is VO n over V in 1. This, according to the, obviously we can imagine to do the same everywhere, and so you end up with the product. Well, yeah, skip it. And using this this symbol, instead of the sum, the product of many factors, from I that goes from 1 to n of I just realized that I've forgot to do a modification here. So this should be, because you see at the last one, there is nothing connected, at least now on this example. So how should I modify this? This is goes to, let me see if this works. This should be this one. All this time, for the last bit, there is nothing attached. So there's no, the last bit, there is no resistor. The resistor is infinite effectively. And so if the input resistor on this side is infinite, the voltage you see is actually the voltage from that. So that remains unaffected. So this is the formula that should work. So it's the product of all these terms for each stage, and just the last one if it is open, like that. Or if there was actually, let's make it more general, if this was over a resistor RL, you could write the last term as RL over RL plus Z output N. Yeah. So now this is extremely powerful, as you can see. We started with one single amplifier. Now we can create really anything we want. We just cascade them, and we know what to expect. So this is for the voltage amplifier. I will give you the. Let's have a break. We started a bit late, so do you mind if we keep it short? Maybe, I don't know, 6 minutes, 7 minutes, something like that. It's 15:02. Let's say 15:10. Okay. In the meantime, I can prepare the bit for the current amplifier.